Have you ever calculated this thing? These things, have you ever calculated and verified that this was true? For let's say some wave function. So your delta x was this thing, x minus x bar whole square and average of that thing. So basically del u square is x minus x bar square. Oh, sorry. This is called del u square. You can take average of this quantity. This will again be an exercise. I will not do it. So you probably did. I'm not sure in quantum mechanics, but you should have done. So you just use this formula for del x minus x bar. So bar in quantum mechanics because it comes like this notation, and then so you do x minus this thing, take square, and treat that as some function of x. So when you do this, or sorry, in quantum mechanics this, then you take this and use the average formula to find out the value of del x over some given wave function. Of course, you need a wave function in that case to calculate expectation because you need mod chi-square. Then do the same thing for p and then multiply, and you will see that this is true. It's always greater than h cross by 2. If you take Gaussian as your wave function square, then you will see that it's exactly equal to h cross by 2, only case when it becomes equal. But the exercise that I'm giving you is not for quantum mechanics. So in general, just you can calculate this quantity for a function that I'll give you now. This is the function that I derived for random walk. So probability of taking nr number of right steps was n factorial by nr factorial n minus nr factorial p to the power nr q to the power n minus nr. This is now your probability, just like p of u. Now you have some w of nr, so nr, let's say. So nr is your u. This is the probability function, and calculate what you have to calculate. Calculate this thing. Easy. Yes. Another thing, the sum of probabilities 1 is easy to prove really. So what will be this sum nr equal? The initial will be that the guy took no steps, and at max it could have taken all the steps towards right. So that's all possibilities. The sum over that has to be 1, and actually it's 1 if you put a sum here and you did nr equal to 0 to n. This thing I told you, this is with the summation, it is just a binomial expansion. The formula for this, so if we put a sum here, nr equal to 1 to n, then this thing is nothing but p plus q to the power n. P plus q to the power n formula becomes actually this. It's a binomial expansion in standard, very standard. If you have two numbers to the power n, then this is the formula. Now, this will be your result if you took a sum. And we know that what are p and q? They're the probability of taking a right step and the probability of taking a left step. If you added them, it's the total probability. So this thing is 1. So 1 to the power n is 1. So at least we just verified that total probability is 1. So where do you have to use it? In the denominator, you do not have to do this summation again. You can forget about it. Just the top part, p of u ui and ui, okay? That way, just calculate for this function, this quantity. Nothing else. This summation was easy because it's just the formula of binomial expansion. But when you put an NR inside now, so there will be summation. And you are calculating the average of NR. So you'll put an NR here. So this is your P of U, and there is an U now. What is U? It's NR. Now the summation is not possible. It's not easy. So in this kind of situation, use the trick. The trick is, so in that case, I'll just tell you. Suppose you had some integral like this. You had dx e to the power some alpha x squared. Okay? You had an integral like this, 0 to infinity. The answer to this is no, you know. It's a gamma function. What is the integration of this? What is the integration of this? Actually, if you know this is very easy. There is a trick. What you can do is, this thing can be obtained if I just took a minus del alpha here. This alpha is a constant. Remember, this alpha is a constant. But treat this like a variable, but not related to x, some other variable. Then if I took a derivative with respect to alpha, x squared will come down, because for this partial derivative, x is a constant. So minus x squared will come out, and this minus, it becomes plus x squared, and then you have your original x squared e to the power minus alpha x squared integral. But now this integration is over x, so I could just pull this whole thing outside. And inside you have just this integration, which will be this function. This is a function of alpha, right? After integration is done, x squared will be gone. It will remain some function of alpha. So here you will have this. Okay? Do the derivative, and that will be your answer. Here something similar is going to happen. Here we have a p to the power nr, and then nr. Do some del p, then this nr will come down, and then take the p outside. The answer to that will be your pn. Anyway, verify that. Answer to the one you calculate will be pn. Now I'm going to introduce the concept of probability density. So discrete probabilities we learned, and discrete probabilities are like, so when I ask what will be the probability of finding the face 3 when you throw a dice, and that will be non-zero something. But if the variable is continuous, for example, this chalk is rolling, so or a ball. Okay, I have a ball that I'm rolling on the floor, so it's hitting that wall, coming back, hitting the other wall again, and it's doing that repeatedly. Then I ask you, what is the probability that the ball will be found exactly at this point, this corner? So these are two walls. The ball is moving in two directions like this. I ask you, so this is 0 and this is, let's say, 10 meters, 6 meters. What is the probability that the ball will be found at, if you randomly looked, what is the probability that it will be found exactly at, let's say, 6.5 meters? Can you guess what will be the probability? It will be 0, because this exact point you are talking about. So let me give you another example, and this will be clear. You have a box like this, okay, and you are shooting bullets into it randomly, just shooting bullets, and I give you a small circle here. What is the probability? And let's say the area of this box is capital A, the area of this circle is A. What is the probability that the bullet will hit this small circle? What will it depend on, the probability? Yes, it will depend on the area. The bigger the area of the circle, higher the chances the bullet will hit inside this circle, right? Smaller the area, smaller the chance. Now reduce that area to 0 size. What is the probability of hitting that 0 radius circle? It's 0. And that question is asking what is the probability that the bullet will hit this point? 0. Just the point. Am I asking? Not the whole. Okay. Yes, the whole thing is 1. If the bullets are not going outside. So this point is 0. Exactly like this when you have a continuous variable. So this ball is continuously moving like this. At least it can be found anywhere. It has some probability. It can be 0, non-zero. But anywhere it has a chance. It's not like a dice or like a coin. So in this kind of situation, the probability depends on the thickness you choose. If I ask you what is the probability to be found between 6 and 6.5 meter, then yes, there is a non-zero chance. The bigger the length, the longer the segment you give me, the higher the probability. When you make it the full thing, it's 1, right? So only asking you what is the probability at this point is 0. So that's why in this kind of continuous variable, we really don't talk about probability. We talk about probability density. And then you multiply by this segment and you get the probability. So in this kind of situation, the probability of finding it, let's say between x equal to some a and b will be this integration a to b, and you need this segment dx and some density. That's our probability density. In quantum mechanics, that mod chi square. That's how we go from discrete to continuous. Now, another concept we already discussed here is this intuition. Actually, you guessed it. There is no proof. There is no theoretical proof that this is what will happen. But you intuitively know. The bigger the area, higher the chances. The smaller the area. So this is a kind of law that we'll formally discuss this, study this later, that the probability really depends on the size of the allowed space, right? In discrete also you saw this. For example, the chance of getting, let's say, 3 out of a dice throw is of course 1/6. But if I increased the space of possibilities, if I tell you what is the probability of getting either 3 or 2 or 5, then you know that it's increasing your probability, right? So this space, this set of 1, 3, and 5 is like that smaller circle. So I'm increasing that thing. So that smaller circle is the allowed space, and so something is more probable if your allowed space is bigger and bigger. And this has a profound connection with thermodynamics. For example, you know the conservation of energy, or the first law of thermodynamics. First law of thermodynamics says that a reaction is not possible if the energy is not conserved, right? Everything respects that. That we know. But then it does not tell you that if energy is conserved, the reaction will be possible. It tells you something is not possible if energy is not conserved. But what happens when energy is conserved? Is it anything that conserves energy possible? It's not. Can you give me an example from thermodynamics that energy is conserved, but it's not possible? We don't see this thing happening. Think about an example. Let's say you have two bodies like this. One is at 90 degrees Celsius, the other is at 10 degrees Celsius. So this is colder, this is hotter. Which way the heat flows? This to that, right? And this is isolated system, just these two things. Heat is not going anywhere else. Why not then the other way around? Will the energy be violated if the energy heat floats from this to that? Energy conservation, will it be violated? I mean, what is the total, let's say, okay, forget about, okay, this is temperature is fine. Initially, this one had energy, let's say EH, and this had EC. What is the total energy initially? Sum of the two. Now when, let's say the opposite way, the heat is flowing. So EC is decreasing, EH is increasing, but the sum is still the same. So the conservation of energy is not violated if the heat flows in the opposite direction, really. You are not taking away heat, you are not destroying heat, you are not generating heat. You are just taking heat from one to the other. I mean, we are not taking. We are asking whether it can do it on its own. But why not? I mean, conservation of energy is not stopping it. First law of thermodynamics does not, but the second law does. And we'll come to second law. But at least energy conservation is not violated, really. It's fine. In fact, you will see that if you look at even Newton's law is your F equal to m square x dt square. Whatever the force is, anything, gravitational, electrostatic, doesn't matter. Anything you take, you'll see that if I put t equal to minus t, that's the same thing. Okay. So Newton's law is okay. So at the bottom level of everything, thermodynamics, heat flowing or whatever, it's just some form of radiation either, or maybe gas particles moving from one box to the other. That way the heat is flowing, right? But they are, of course, following either classical mechanics or quantum mechanics. And at the bottom level, these two allow backward motion in time. So in principle, we should see things, heat flowing from colder bodies to the hotter ones. It should be visible. Or let's say I drop a glass of milk or whatever, and it falls and it, splashes and it shatters into pieces. Then we should also see these pieces coming together and forming the glass back to my hand. It's not forbidden by our laws of physics, really. Classical mechanics or quantum mechanics do not forbid this. In some universe, this should happen, but we don't see it. And the thing is, actually, according to physics, this is possible. This might happen. But why we don't see it? The most accepted theory is that it's highly, highly unlikely. So the chances of that happening is so rare that it might take a time longer than the age of the universe. If you waited that much and repeated this thing, maybe someday the glass would come back to your hand and you would age backward, you would get younger or whatever. Okay. So what gives the time its arrow? It's called the arrow of time. The time always flows in the forward direction. We get older, things get broken. So everything goes towards slightly disordered state. That we know. For example, if you had a perfectly organized library room, your table, let me do it here so that otherwise they will not see it. Let's say you have a table like this. You had 3 pieces of chalks like this. You organize a duster here, maybe a book here. Okay, a pen here, perfectly organized. This, 2 pens, let's say. If I slightly change the configuration, you will know, right? You will know. So it will be very different. But suppose the chalks were like this, the duster was here, another book was here, the pens were here and here. And then I make slight changes. You will not know the difference. Okay? A room full of books that are scattered everywhere. Then which book was here? I might just take one book from this place and there, and you will not see the difference. So the state of disorder has more, how do I put this word? Has more possibility, allowed. So it's like increasing the size of that circle. If you understand, let me repeat. Okay, so you can change this room in many ways, but it will still look the same. Okay, it will still look the same, more or less. But if you took a very ordered room and you made slight changes, it will look very different. And that means you're allowed, so number of ways you can make changes is more for disordered systems compared to ordered. And because there are more allowed ways, the allowed ways for a disorder is more, the system, the probability of that is more. Okay? It's like, so very ordered means really a point. This is exactly where you have to hit the bullet. The slight change, and it's not this point anymore, it's another point. But then I tell you, okay, hit anywhere inside the circle. As this gets bigger, the chances of bullet hitting this is higher. So exactly a disordered room is like you have many possibilities, the ways you can change, and still you will have the outcome that you desire. This is how the room looks like. So it has more probability of going into that. And that's why everything go towards disorder, really. You organize your room and you come back after a month, you'll see like nobody touched, but still there is dust, something decaying, some maybe insects had eaten up your book, or like maybe weather, it will go towards disorder. You have to put some constant effort to keep it organized. And this law is actually, this is a law of probability. And this applies everywhere, even in human relationships. A family that does not put constant effort in keeping the relationship, respecting the relationship, they will go towards divorce, or like even simple relationship, boyfriends and girlfriends. If you don't go to like organized dates and like gift and respect, if you don't work on it, it's going towards breaking up. So it's like a disordered state. Breaking up is more probable. Okay, if you don't do anything, then it's more highly likely that it's going towards a breakup. So this law really applies to everything, not just it's simple. Like something has more allowed possibility, so something will go towards that. That's the law of entropy. We'll do that in details, but this is the gist of it. That the a glass falling and shattering is going from ordered state to disordered. Those shattered pieces are more probable. Okay, there are many ways you can organize those shattered pieces, and it will still look the same. But for a perfect glass takes a lot of effort to form this perfect shape. This is highly unlikely. And so this form, going back to this, is still possible, but very improbable. And that's why you will always find things going in that direction, not the other way around. So that was the law of entropy, or more or less the second law of thermodynamics, really. So that entropy of the universe always increases, tends to increase. Things always go towards disorder. So here actually I indirectly introduced the concept of microstates and macrostates. In this particular example of the library, all those books, shattered books, disorganized, their locations, like one particular organization, let's say this quantum mechanics book was on that corner, thermodynamics book was on that chair, that one organization is one microstate. Then your friend comes, you have no idea, he maybe changed some of the things to slightly different states. So this book now is there, and that book is there, that another microstate. And this way, all these possibilities are different microstates. What is macrostate? How on the average the room looks. That's your macrostate. Now the macrostate that has larger number of microstates is going to happen more. So if your room is very organized, that room, that macrostate has very less number of microstates. Slight changes and it's not the same room anymore. So it's not the same macrostate anymore. Okay, a disordered room is the same macrostate, but it has a large number of microstates. Many changes you can make without changing the average look of the room. So the heat flowing from a lower body to the higher is related to that. Okay, that's the way. So it's related to this. Let's say you have a box, and here at the corner, I release a bottle of gas, let's say. So at this point, corner, and now they are slowly spreading out. Over time, they're slowly spreading out. So this going to, so this spreading out is again another phenomena of going from less ordered state to disordered, because this thing has really very less number of microstates. The particles can be here, only in this smaller space. But in this case, you could take this particle, put it here, this one there, okay? So you have this large volume. So large number of possibilities where you can put these gas particles. And each such arrangement is a microstate. And on the average, how the room looks, is the box looks, is a macrostate. Now when they are perfectly spread out is the final state. The highest space they have covered. So really the highest number of ways now you can change and the room will look the same. While this state is really not that much. I mean, you put it from here to here, it's not the same macrostate anymore. You will clearly see, okay, if the gas has a color, like blue color, let's say. Now, it's not the same, it was in that corner. But once they're spread out, it's like slightly bluish all around. Now, where each one, I mean, this gas particle is there or this one is there, doesn't matter now. It's the same macrostate. And therefore, gas in this state where they're spread out is much more probable than gas being just here, because this is less probable, which means now more probable state will be attained by nature, by universe. So that's why these gas will move out like this. The other possibility is all these gas suddenly going towards the corner and becoming like the initial state coming. That's like going from more probable towards less probable. It's very unlikely. You can calculate this. I'll give you this problem. It's very unlikely. You will see that it's almost zero, the probability of happening. But probability of happening in this direction is huge. And so you will say this is highly likely. Okay. So this is more or less the concept of microstate and macrostate, not the formal one. let's forget about quantum mechanics. Let's say the gas molecules are not fast enough, so not relativistic, and let's say they are not interacting very well, so that quantum mechanics, let's say, don't apply. Classical. Then we have we have Newton's law. Newton's law is just say F equal to ma, and that's just a collection of actually 3 equations, right? That's a vector, so basically 3 equations. And let me write it down in this form. So that's a collection of 3 equations. So 3 equations you have, 3 scalar equations, x in x direction, y direction, and z direction. And when you solve it, it will have 2 unknown constants because it's a second order differential equation. Once you integrate, you will get a C1. Again, you integrate, you will get a C2, right? Plus C1 plus C2. So the second order. So 2 unknowns. To fix them, you need, like, at time t equal to 0, what was the position? Then you find maybe C1. At time t equal to 0, what was the velocity? Then you find C2. So anyway, to solve this perfectly, you need 2 initial numbers. Okay, that's fine. But once you do that, you basically have this R and V, right? Forever. You know R and V forever. Once you know these constants, you can tell where it will be. So R is X, Y, and X, Y, and Z, and this is Vx, Vy, Vz. Once we know this, things are fixed. Now we can tell where it will be. So these are 6 numbers, and if there are n number of particles, then 6n for each one of them. So 6n numbers. So that's like the situation here. Any state, any screenshot of this is knowing 6n numbers, where they are and what is their velocity. You can pick one of them, bring it here, and give it some other velocity. That way you can organize. So knowing this one value of this 6n is 1 microstate. One set of these values is 1 microstate. Another set of these values, another microstate. If it's simple, if I say there are only 3 particles, and this is 1 microstate, this one is moving in this direction, maybe this one this way, this one this way. Okay. Just for an example, 3 will not really do, because once you have just 3, then slight changes will be visible, and then it's not the same anymore. But just for an simplicity, now this can be like I bring it here, and this one here, this one here, that's another microstate, and the average thing is a macrostate. That's it for today.